Okay, so welcome to Math 310 Modern Algebra. This is lecture 3. And so what I want to do today is I want to talk a little bit about the pirate riddle as a way to segue into group theory. And then we'll start doing group theory. I'm going to turn Thursday's class into a general all math review for anything in your math career up to and including abstract algebra. Okay, so there will be no class on Thursday. We will just have individual meetings by Zoom at your convenience. So if there are any questions you have on any material in any of your classes, from anything from, we'll say kindergarten to here, let me know. And then this way I can personalize things a little bit. If we want to do things in groups, I'll post topics at 10 o'clock on this day. We're going to be covering geometric series, series convergence, stuff like that. So that, I know different classes have covered different things. I know not everybody has taken the same classes. So let's just have one review class and just get everybody up to speed without having too much new material coming at you. So we will do that. All right. So let me just quickly review the rules of the pirate riddle. There are 5 pirates with the wonderful names 1, 2, 3, 4, 5. There are 100 gold coins that must be split, and you have to give somebody an entire coin. You can't give somebody part of a coin. The lowest named pirate alive proposes a division. If 50% or more vote for the plan, it passes, and you so divide. If over 50% vote against, the plan fails. Whoever proposed is killed, and the lowest named surviving pirate proposes. You keep until a plan is accepted. Assume the pirates are intelligent. They are graduates of Siena after having completed Math 310. They are thinking pirates. What happens? And again, some of this depends on how you do voting. If you're following politics in New York City right now, you see things can really depend on how you do voting. The way we will do voting is people will discuss as long as they want, and then once everybody agrees to vote, you will write your vote, yay or nay. Do you approve or disapprove of the plan? In a secret ballot that nobody else sees, you put it in the cauldron, and then they're turned over. And so all that happens is at the end of the day, you know if a plan passes. You do not know how people voted. So for instance, if Pirate 1 proposes something and it fails, it might be useful for Pirate 2 to know, did people say that they were going to support the plan and not? Is somebody a lying piece of shit that I'm not going to trust them because they've already burned somebody? You don't know that. All you know is, does the plan pass or fail? Does everybody understand the rules? And when we're done, I will let somebody play me for an A+. All right? Does anybody have a thought as to what happens? How should we analyze this game? How should we do this? Yes. So you want to start with Pirate 1 proposing something. I think that's a good thing to try, but that's the wrong thing to do. Just because I've asked this question, does this mean that this is the first question you should try to answer? No. Gather data. Try to study something simpler. What would be simpler than studying 5 pirates? 1 pirate, right? So let's play a smaller game and work. So what should the name of the 1 pirate be? Fine, excellent. 1 pirate. Number 5. All right. This is probably, for those of you who are uncomfortable speaking up, the most softballish question I can possibly give you, the most marshmallow question possible. What does Pirate 5 propose? Yes. Number 5 says, I get all. What do you think? Passes or doesn't pass? Passes. All right. We have completely analyzed the 1 pirate case. Building on this remarkable success, what should we do now? 2 pirates. And they're named number 4 and number 5. It is not quite as much of a softball question, but it's pretty close. What does Pirate 4 propose?
100% to himself.
100% to himself. Number 4 says, I get all. Number 5 gets none. What do you think? Passes. How do you think the people vote? Yeah, 4 says yes. I like this plan. I'm excited to be a part of it. Cultural extra credit if anybody knows the movie that's from. I love this plan. I'm excited to be a part of it. Pirate 5 says no. It passes. All right, now what do we do? 3 pirates. And their names are 3, 4, and 5. So now maybe things are going to get a little bit more interesting. So 3 proposes. So some number for 3, some number for 4, some number for 5. And it's okay if your suggestion doesn't pass. Can somebody give me some possibilities?
50% to 3 and 50% to 5.
Okay. So, and how much to 4? 0. What else? Can somebody give me another proposal? Okay. Any other proposals? There's at least one other type of pirate.
32, 32.
Yeah, and who gets the extra one?
I guess. So.
Yeah. Thoughts? Second one. If pirate 3 proposes 50, 0, 50, what's going to happen? Passes. Who's going to vote in favor? 3 and 5. And 4? Well, is 4 going to vote in favor or not? No. What happens if this proposal fails?
We're gonna make the 2 pirate game happen again.
So if this fails, we go to the 2 pirate game. Pirate 4 gets everything. And Pirate 5 knows that. Pirate 5 knows that if this plan fails, we go to the 2 pirate game. What happens to Pirate 5 in the 2 pirate game? They get nothing. So Pirate 5 has I think, an aligned interest with Pirate 3 here. What about the plan 9901? Passes or fails? Passes. Why? Okay. What about the 3, 4, 5? So I think 3 is going to vote yes. 5. What about 4? 4 will probably vote no. Right? Even though you're giving 33, 4's like, if this fails, I get everything. I'm going to vote no. Okay. So what should we study next? 4. So what do you think the proposal is going to be for 4 pirates? So you're going to do 99010. Why?
Because in the next round, 4 gets nothing.
In the next round, 4 gets nothing. Right? So 4 realizes that if I don't vote for this, I'm screwed in the next round. So I think you're going to get the votes of, and what about 3 and 5? And after the 4 pirate game comes finally the 5 pirate game. And so now we have 1, 2, 3, 4, and 5. What proposal do you think you're going to get? What do you think? 98. And who's going to vote in favor? Obviously, the people who are getting the stuff. How can I split the pirates? Odd and even. This is a parity game. All that really matters are which group are you in. The pirates have basically been split into two equivalence classes, the even pirates and the odd pirates. The even pirates are aligned, the odd pirates are aligned. And this is a great way to handle a lot of problems. Just because something is given to you does not mean that's what you should look at. Try to find something easier first, build some intuition, get a sense of how to attack the problem, and then move on from that. All right, who would like to play me for an A+ for the semester? Okay, one of the Elizabeths, excellent. I need one other person just to be pirate 4. Need somebody else. I need one more pirate. Yeah, okay. Thank you, not Elizabeth. All right, who am I playing? Playing Elizabeth. What's your proposal?
In general?
Yep, just sling up the 100 points.
Oh, okay.
Yep,
What are the needs?
same as before. You need a majority.
Okay. All 6, 99.
Uh-huh.
And we're going in this order?
Yep. Elizabeth, not Elizabeth, not Elizabeth, also known as Miller.
And we have to play smart. Does Claire have to play smart?
I would assume so. I mean, this is a 300 level class. How long have you two known each other? Okay. And how much do I get? Okay. We now discuss this. Why should I support your proposal?
Because Claire's gonna take it all from you. He's really greedy like that. So you don't wanna get to the.
I mean, the federal regulations really restrict what faculty can see about students. I can't tell how greedy you are from the, I mean, I can tell your middle name, but social security number, but it doesn't have anything about greedy. Are you greedy?
She is. Yeah.
And a ventriloquist too. Are you trustworthy? Wow. Okay.
But I'm really trustworthy.
Well, I mean, you're offering me one, and you know, if I don't take your deal,
Yeah.
I get nothing. All right, class, what do you think I should do? Take it or leave it?
Take it.
Take it. How many people say I should take it? How many people say I should leave it? Well, yeah, of course, you should say I should leave it. And what should you tell me?
That'll give you everything.
Exactly. Or at least I'll give you 50, I'll split it evenly. And then you screw me later, right?
Probably.
No, I mean, you're honest. I mean, you know, if you said no, I wouldn't trust you, but you know, you're being honest about it. Anybody ever see My Cousin Vinny? All right, I'm going to make you a counter offer. Okay, here's my counter offer.
I thought you said we were going in that order. Doesn't
Yes.
matter if it's a counter.
Well, no. I'm saying this is what I think you should propose.
Oh, to you.
Yeah, I'm saying, Elizabeth, I think instead of the 9901, I think you should really rethink that. I think a much better proposal for you, and again, it's your choice. I think you should propose 0000. So why am I going 0, 0, 100? Who thinks I'm crazy? I must have a reason for doing this. Think outside the box.
You'll say like, you're only gonna vote yes if I give you 100, and if I don't, then I'll die.
Then you will die. Yes, because if your proposal doesn't pass, so it's 9901. That's your initial proposal. I said, no, if you do that, okay, yes, I get 1, which is better than if it goes to Claire. But I think you should do 0, 0, 100. Now you have two possibilities. You have a couple of possibilities. One possibility is you can say, you're right, and I'll take 0, and I'll give you 100. You could try to form an alliance with Claire. Okay. And so what could you propose to Claire?
I'll split it.
And Claire can say, and Claire could say yes. And then what can Claire do when we vote by secret ballot? Screw you, because Claire knows that if the plan fails, she gets everything. So can you trust anything Claire says? No. So you are welcome to try to form an alliance with Claire, who you told me is not trustworthy and is greedy. I'm just saying what you said. You said she was a non-trustworthy, greedy pirate. So if you want to try to form an alliance with Claire, go for it. But if I was Claire, I would screw you and then take everything. So how do you propose to, what do you respond to my 0, 0, 100?
Say, how about 50-50?
So you will propose 50-50? You blinked. So in negotiations, a lot of times, whoever blinks first loses. You just moved from 99 to 50. You didn't hold hard and said, I'm staying with 99. I think that's not a bad idea for you to blink. I will counter. No. I'm going to be reasonable. I'm going to counter with 49,051. And if you don't like it, you die. Is that 1 coin worth it? You are already at 50.
Yeah, it is.
So you're going to hold out for the 50?
No, I'm going back to 99.
So you're going to go back to 99. So then, again, you are absolutely welcome to do that. And again, this is where it kind of sucks that we're not doing this for real and I can't actually kill you. No, because this is a hypothetical. This is a hypothetical, right?
But don't you care about money more than you care about killing me?
But I can say the marginal benefit of me going from 0 to 1 is so small that it's really not that big of a deal. But going from 0 to 50.
Maybe these coins are really valuable and 0 to 1 is like.
It could be. It could be. So what would you counter if I then say no? I will go back to. I'm running out of space. So if we had something like this. I think I can resize it to almost have a little bit more space. There you go. All right, so I will then come back. With 0, 0, 100. You went back to your old, I'm going back to my old. It's not clear what the answer is. It depends on the person. Yeah.
But you know for a fact that if you say no, and Claire's going to say no because she gets nothing,
Right.
then you're guaranteed to get nothing anyway.
I am guaranteed to get nothing.
Why would you do that when you know that you're going to get nothing? Elizabeth said.
It's who blinks first. So part of this is to prepare you all for the real world. When you do negotiations with people with companies, A lot of it is bluff. If you've ever watched poker, if you've ever done anything like this, there's a difference between math and the real world. And so everybody, you did the analysis great. Take a difficult problem, build it up from a simpler problem. Let's do just 1 pirate, 2 pirates, 3 pirates, reduce the complicated problem to a simpler one. A lot of it is going to come down to who blinks first, Elizabeth or myself. And who has more to lose. Elizabeth has a lot more to lose. So I could do the following. Instead of doing that, I will propose the following, Elizabeth. You ready? 48, 0, 52. I'm not going to be extreme. I'm not going to go to asking that I get everything. Every time you delay, it's going to cost you a gold coin. The longer you delay, the less you're going to get.
That's fine.
So would we accept this?
No.
Nope. So you're going to propose again? You're going to go back to the 9901?
Yeah, I guess.
All right, then if you do that, I will propose 47, 0, 53. And we're going to just keep repeating?
I know, what I'll say is final offer is my 9901, and you can take your 0 coins if you want to kill me off that bad.
Okay. Elizabeth fails class due to death. And a lot of times people get to the point where they just can't back down. How many of you have taken probability? There's a great game of I have $1. Whoever bids the most gets the dollar. Have you heard this? And do you know what the other part of the game is? Whoever bids the most gets the dollar.
When you get a start bidding at 1 cent or something, and then, people have to take the opportunity of getting the.
No, but there's something else. There's another rule that I'm not telling you about the game. Whoever bids the most gets the dollar. Whoever bids the second most has to pay that. So if you think about it, would you bid 50 cents for $1? So somebody bids 50 cents, I'll bid 51, 52, 53, 54. And now we get to $1. Let's say I bid $1, you've bid 99 cents. If you don't get the dollar, you're out 99 cents. So you'd bet $1.01, which means I would now bet $1.02 because I don't want to be out $1. And you can get to this ridiculous situation where you're now bidding more for the dollar than the dollar is worth because you don't want to be in the second place. There's a lot of great stuff like this in terms of how do you analyze something like this. In the real world, when you try to apply mathematics like this, the theoretical analysis is great if you're playing with completely rational people who are upfront and honest.
But not when you're playing with Claire.
I would say with Claire or people to the left of Claire. That when you're doing something like this, it's who blinks. And can you convince me that you're not going to blink? If I am absolutely convinced that you will only do 9901 and you keep doing that, then I might blink. And I might say, I tried to bluff you and you held firm. This is why I was trying to do a very small penalty every time you did it. There's a lot of games like that where they give rewards and whatnot. And so again, this is not directly related to groups, but it's this idea of how do you attack a problem. And I know a lot of you are thinking about careers in education and talking to students. How do you attack a problem? How do you analyze? There can be more than one right answer. And so when you're looking at stuff like this, it's a wonderful problem in terms of how psychology now comes into play. And so it's not clear where you would end up for something like this. But if you ever look at trade negotiations or salary negotiations, a lot of times it's who blinks first. And can you convince somebody that you are willing to walk away? All right. So let's shift now to some stuff directly related to modern algebra. So we're now starting chapter 2. This is the introduction to group theory. So we talked about permutations before, So if n is a non-negative integer, 0 factorial equals 1, and n factorial equals n times n minus 1 factorial if n is greater than or equal to 1. And there was a nice interpretation to that. N factorial is the number of ways to choose, to order an object. You have n choices for the first, n minus 1 for the second, n minus 2 for the third, all the way down to 1 choice for the final. So there's a nice interpretation for something like this. So why do we care about n factorial? It turns out that there's a lot of things in mathematics that can be defined by factorials. Can someone tell me what 3 factorial is? 6. 3 times 2 times 1 equals 6. What about 3 double factorial? What would that be? So one possibility, it could be 3 factorial factorial, which would be 6 factorial, which would be 720. But actually, n double factorial is defined as n times n minus 2, n minus 4 dot to dot down to either 1 or 2, depending on whether or not it's even or odd. It's a definition. When you write double factorial, it's not clear. Do you mean the factorial of a factorial? Or is the double factorial the function? It turns out the double factorial occurs in a lot of things in mathematics. How many of you have taken a stats class? If you've seen the normal distribution, the bell curve, the Gaussian, the double factorial comes into play for the moments of a Gaussian. The even moments, the 2nth moment is 2n minus 1 double factorial. There's a geometric interpretation, there's a combinatorial interpretation for n double factorial. We can define anything we want. So what would this be? My favorite number is 3 exclamation point, exclamation point, exclamation point. How would you read that sentence? What's my favorite number? So it could be my favorite number is 3, and I'm just damn excited. Right? How else could you read it?
0.
I don't think you can read it as 0. So you could say the 3 exclamation points is just expressing excitement. That's one possibility. How else could you view it? Every sentence has to end with what? A punctuation mark. So you could view it as 3 factorial factorial and then punctuation mark. Right? I could view it that way. My favorite number is 3 and I'm really excited about it. Or my favorite number is 720 and I'm also excited about that, but not as excited as if it had been 3. This is really bad notation. You want to stop and think, how are we defining things? Why are we choosing the notations we are choosing? I'm not sure if this counts as a word. Can anybody talk to me about QWERTY? Yes.
Top 6 letters.
It's the top 6 letters of the keyboard. Why are the top 6 letters Q, W, E, R, T, Y? If you were designing a typewriter or a keyboard, is this how you would choose? In what way? Not quite, no.
So
It was made during the typewriters, when there were many typewriters. They actually kept newsletters apart so that they wouldn't clog each other.
Right, so in the old typewriters, you actually had physical things going down and striking the paper. And if you hit two things on the typewriter close to each other in quick succession, they would jam. So the whole point is to try to get you to alternate between left hand and right hand. It's to slow you down. Nobody does anything like this anymore, but it's been institutionalized. And so you really want to think about what you're doing. There is a very natural reason why we have a QWERTY keyboard. It's now, we're stuck with it. If we really loved our children, what would we do? We would switch to a better typewriter. Straight alphabetic is faster. Dvorak is what professional typists do. But that would require work on our part. We don't love you that much, right? And so it's worthwhile whenever you choose notation, really think about this. How many people here have not sent an email in their life? Okay, what does CC stand for in an email? Carbon copy. This goes back to the time when you had, where you made copies that you would write down really hard on it. There'd be a piece of carbon paper underneath, and it would press into another piece of paper. There's no carbon copies in electronic email. Some people have changed CC to now stand for courtesy copy, but it's often still said as a carbon copy, even though it's way beyond that. Think about the notation you want. There's a lot of ways to know things. So if I have n objects, there are n factorial ways to arrange them. So one possibility is if I can give the numbers 1, 2, 3, 4, I could say maybe 1 goes to 2, goes to 1, 4 goes to 3, okay, 3 goes to 4, 4 goes to 6. This is one way to represent what's going on. And sometimes you might write that as 1, 2, 3, 4, 2, 1, 4, 3. And so this would be a nice compact way of writing things. Another way we could write this is we could write it as 1, 2, 3, 4. And this 3, 4 means 3 goes to 4 and 4 goes to 3, 1 goes to 2, 2 goes to 1. And if I gave you 1, 2, 3, 4 goes to 2, 4, 1, 3, I could write this as, just, 1, 2, 3, 4, 2, 4, 1, 3. And then I could write it as 1 goes to 2. What does 2 go to? 4. What does 4 go to? 3. And what does 3 go to? Good, and it wraps around. So these are different ways of representing the same thing. I could try to write this in a matrix form. So I want 1 to go to 2, 2 to go to 4, 3 to go to 1, 4 to go to 3. So imagine I take 1, 0, 0, 0. What is that supposed to go to? So if I'm using the one above, what should 1 go to? Okay, and what would that be on the right-hand side? What vector? What vector should correspond to the 2 vector? Now, the 1 vector was 1, 0, 0, 0. What should the 2 vector be? Not 2, 0, not 0, 2, 0, 1, 0, 0. So when I have a vector like this, which columns will I get information about the matrix? Which columns will I get no information? So everybody's taken linear algebra, correct? So which columns am I going to get no information about the matrix when I apply it to 1, 0, 0, 0? I'm sorry, the ones with zeros. So which columns, first, second, third, fourth, which columns does this give no information? So when I apply 1, 0, 0, 0 to this matrix, I'm trying to sniff out the elements of this matrix. Which columns do I have no information from applying 1, 0, 0, 0 and getting 0, 1, 0, 0? Second, third, and fourth. The way I do it is, I have my first column here, and that's going to hit the 1. Then I have the second column, and that's going to hit the 0. Then I have the third column, and then it's going to hit the 0. Then I have the fourth column, and it's going to hit that 0. So the second, third, and fourth, I'm going to get no information about. Now for the first column, I've got to go 0, 1, 0, 0. So I have no information here, no information here, no information here. What does the first column of my matrix have to be? If I want to get 0, 1, 0, 0 when I apply 1, 0, 0, 0, what has to be in the top left? It has to be a 0. What about the next one? The first element of the second row, what does that have to be?
1.
Has to be a 1. And then the next two things have to be zeros. So if I take this matrix 0, 1, 0, 0, doesn't matter what I put in the other 3 rows, that's going to take the vector 1, 0, 0, 0 to the vector 0, 1, 0, 0. All right, so this is sending 1 to 2. Well, now I could try to send 2. What does 2 go to? So if we're using this, what does 2 go to? 4. And now what vector would 4 be? That would be the 0, 0, 0, 1. So notice, because my vector starts with a 0, it doesn't matter what I have in the first column. Do I get any information about the third or the fourth columns? No, they're still all zeros, so I get no information there, no information there. But I now get information about the second column. And so I want to get 0, 0, 0, 1. What do I have to get for the second column? So what do I have to put in the first element of the second column so that when I multiply by 1, I get 0? I have to put 0. What do I put in the second entry so that when I multiply by 1, I get 0? 0. What about the third entry? And the fourth entry? 1. And so I can keep playing this game. And then the next one, what does 3 go to? So 3 goes to 1. So what do I have to get now? So what do I need to get for the next one? I want to get 1. So what should the first entry be? What should the 1? And then all zeros. And then the last one is we have to figure out where does 4 go to. And 4 goes to 3. So what does the last column have to be? It's got to be 0, 0, 1, 0. Question? If this isn't clear, please speak up. What we're doing is this matrix sends, so the matrix 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0 sends E1 to E2, And what does E2 get sent to? It's sent to E4. What does E4 get sent to? E3. And what does E3 get sent to? E1. This is another way of representing the permutation. This is another way of representing the map that sends 1 to 2, 2 to 4, 3 to 1, and 4 to 3. I can represent it as a matrix acting on the vectors E1, E2, E3, E4. And the advantage of this is now you have some tools from linear algebra that you might be able to use. Okay. So this matrix has some interesting properties. What do you notice when you look at it? What can you tell me about it? So what patterns do you see?
It has only one ones in each row.
So each row has only one 1. What else? Each row has only one 1. I'm sorry?
Like when it's symmetric.
So to be a diagonal matrix, you only have non-zero entries on the diagonal. It's symmetric if what's above the diagonal is the same as what's below. If Aij is AjI. So it's not symmetric. But knowing what it isn't is also as good as knowing what it is. So it's not a symmetric matrix. It's not a diagonal matrix. Every row has exactly 1, 1. What else? Each column has exactly 1, 1. Yes. It is a permutation matrix. And then you can ask, how many permutation matrices are there? Well, how many permutations are there of 4 objects? 24. There should be 24 such matrices like this. And you give me a permutation matrix, and I have a way of finding out what it is. Why is this useful? Who cares? Right, this is one of the questions you always want to ask. Who cares? If I give you a permutation, I can apply the permutation. And then I can apply another permutation. And then another and another. How do you figure out if I want to apply this permutation and then this permutation, what happens? Well, if I apply this permutation, 1 goes to 2, and then 2 goes to 4. 2 goes to 1, 1 goes to 2. So I could figure it out by chaining things like that. This is just another way of writing it. I can write this as, what this means is 3 goes to 4 and 4 goes to 3. 1 goes to 2 and 2 goes to 1. It's the same thing as the red thing, yes. And then for the next one, I can write this as just one long chain. 1 goes to 2, goes to 4, goes to 3. What we're seeing is there's many different ways of writing things. And some ways are a little bit easier or more conducive than others. If I wanted to figure out what happens if I apply the first permutation and the second permutation, so let's call this maybe P1, and let's call this P2. If I wanted to calculate P1, P2, I have to figure out what does everything go to. Well, P1 sends 1 to 2, and then P2 sends 2 to 4, so 1 would have to go to 4, right? P1 sends 2 to 1, P2 sends 1 to 2, so 2 goes to 2. Oh, 2 is left fixed. P1 sends 3 to 4, and then 4 goes back to 3. And then 4 goes to 3 with P1, and 3 goes to 1 over here. So if I want to find P1, oh, sorry. I wrote this the wrong way. This is P1 followed by P2. You have to be very careful which order you write things. This means first I do P1, then I do P2. How many of you have done multivariable calculus? Everybody should be raising their hand, right? If I want to take the second derivative with respect to x and y, d squared f dx dy, does that mean I take the derivative first with respect to x and then y, or first with respect to y and then x? Or do I say I only look at functions that are twice continuously differentiable, so these two are the same, the mixed partials are equal, and I don't have to worry about that? It's really nice not to have to worry about it, but you have to define the notation. Is d squared f dx dy first differentiate with respect to y and then x, or first differentiate with respect to x and then with respect to y? You have to be clear about your notation. When we write things, we always start from the right and move outward. We do P1 first and then P2. And so this is the same as 1 goes to 4, 2 goes to 2, 3 goes to 3, 4 goes to 1. So this is really the same. I could just write this as the cycle 1 goes to 4. And when a number is not present, it basically just means it goes to itself. This is a lot simpler to write 1 goes to 4. The advantage of using permutation matrices is if I have a permutation matrix for P1 and a permutation matrix for P2, if life was good, P1 followed by P2 would be the matrix P1 multiplied on the left by the matrix for P2, and that is true. So this becomes a convenient way to study a lot of finite groups. Is if I give you a finite group, every finite group turns out to be a subgroup of the permutation group. If I have infinite groups, things get a little bit more complicated. Okay, so we are now ready to define a group. So a group consists of a set G with a law of composition. So what that means is we have a way of combining elements in pairs. And so there's a lot of ways to write it. So I give you two elements, G1 and G2, and then I get some new element, G1 dotted with G2. Sometimes instead of a dot, people use a plus sign. Sometimes people also you can use a plus. Sometimes they use a circle around this or a circle around a plus to just remind you that it's not necessarily the same plus that you are used to. Who knows what 13 plus 97 is? What's 97 plus 13? You should be able to get that immediately now that he gave you 13 plus 97. Why is it easy to get 97 plus 13 once you know 13 plus 97?
Addition is commutative.
Addition is commutative. So whenever we use a plus sign, we usually reserve the plus sign for groups that are commutative. It's just good notation so you can quickly glance down. If you're doing calculus and you have the function f and you have a function big F, what relation do you think is true between those two functions? If the professor has good notation, what should the relation between big F and little f be in a calculus class? Yeah. If that's not the case, you are allowed to sue the professor. I actually had a math class where f on the left-hand side of the equation was not the same as the f on the right-hand side of the equation. We called foul on that. So if I give you a group, I have to give you a composition law. So for instance, maybe I'm looking at permutation matrices. These are matrices whose elements are 0 and 1. Each row has exactly 1, 1. Each column has exactly 1, 1. And my composition law might be matrix multiplication. And so I have to give you a set, and I have to give you a way of combining elements of that set. Okay. So 4 things must be true to be a group. The first is the identity axiom. There is some element, which we will denote by E, such that E times G is G times E is G for any G. Basically, there's an element that does nothing. If you think of multiplication, what should the identity element be for multiplication? 1. What should the identity element be for addition? 0. All right, so we want our group to have an identity element. The next is the inverse. You give me any element G, and I can always find some element H, such that G times H is H times G is E. Okay, so there's an inverse under the composition law. So if you're thinking multiplication, what would be the inverse of 2? A half. If you're thinking addition, what would the inverse of 2 be? -2. All right, so the next, and we denote this by g to the -1 for g inverse. So the next is the associative law. And this is where people often use their g times, I'm sorry, g1 times g2, g3, right, is the same as g1, g2 times g3, like the dramatic form, okay? What this is basically saying is life is good. You don't have to worry about how you group things. I can combine G2 and G2 and G3 first, and then G1, keeping things in the right order, or I could combine G1 and G2 and then combine G3. Remember, our composition law is a binary law. It has 2 inputs. It would be terrible if these were different answers. There are extensions of the integers where, unfortunately, you don't have associativity. So this is not always the case. In everything we look at, this is going to be the case. Okay. And then the last and optional feature is the commutative law. If G1, G2 is the same as G2, G1, then G is said to be commutative or abelian. And the abelian is after the mathematician Abel, or Abel. Now, if you look at this, there are 3 items that must be true for a group. There's really a 4th thing, but the way the book has written it, that 4th thing is kind of hidden over here. Unfortunately, I need a letter before A. So I'm going to just call it maybe 0, and I'll call it the closure action. G1.G2 is in G for all G1, G2 in G. So if I give you a set, if I take a combination of 2 objects from that set, I stay in the set. This is implicit in how it's defined. A group consists of a set G with a composition law, taking G cross G to G, taking pairs of things in G and giving you something in G. We've put the closure in the definition. So it's all a question of just where do you want to have the word closure? Do you want to have it as part of the definition where you are defining your map, or say, I have a set, I have a rule that takes things in the set and gives me something new, and I want that to stay in the group. Okay? So there's a lot of basic properties of groups. Every group has one identity element and only one identity element. It's unique. You don't have 2 identity elements. Each element has exactly one inverse. If you have 2 elements, G and H, then the inverse of G times H is the inverse of H times the inverse of G. And the last is the inverse of the inverse is itself. So we will prove a bunch of these. Do any of these seem obvious or reasonable? Which one seems reasonable? D, right? I have a remarkable ability to keep a straight face at various times. And a couple of years ago at Williams, the student newspaper was asking a bunch of professors, what is your favorite number and why? And this was before I became president of the Fibonacci Association, but I was still involved. And I said, the golden mean, which is 1 plus the square root of 5 over 2. Very important in Fibonacci numbers. And I said, the reason I love the golden mean so much is phi is the reciprocal of its inverse. What's the reciprocal of phi? That's 1 over phi. And if I take the multiplicative inverse of 1 over phi, what do I get? P. Can you give me another number that is the reciprocal of its inverse? Every number? There's one number you have to avoid, 0. Anything other than 0 works. And I said that with a straight face, and they published it. As you see, all these other mathematicians have their favorite numbers with nice justifications as to why this is their favorite number. And I have the golden mean because it's the reciprocal of its own inverse. If you think about what's going on here, the inverse of the inverse, you should be returning to yourself. Who remembers arctangent? What is the tangent of arctangent of x? X. That's basically what we're doing with D. So D is at least reasonable. If you've taken linear algebra, one of these should remind you of something from linear algebra. We're down to A, B, or C. There's an operation in linear algebra that looks like one of these. Matrices. What operation for matrices switches the order? There's 2 good answers. The blank of a product is the product of the blanks in reverse order. You've seen something like that in linear algebra. Anybody remember what the operation is? You're going to kick yourself. You want to try? Do you have a guess?
No.
So there's 2 answers. One is the inverse, right? The inverse of a product is the product of the inverses in opposite order, just exactly like what we have here. The other one is the transpose. The transpose of a product is the product of the transposes in reverse order. So this hopefully looks like something you've seen before. Okay. The last is each element of G has exactly 1 inverse. That seems like a really good property to have. I shouldn't have 2 different things that are my inverse. And I shouldn't have 2 different identity elements. I am going to just make an advanced comment. For any of you who are considering graduate school or whatnot, there is a bunch of different games mathematicians sometimes play to impress each other. Have you ever seen the TV show Name That Tune? Anybody? So they basically compete for money, and they're going to play a clip of a song, and they give you some information about what it might be. And it's, I can name that song in 5 notes. I can name that song in 3 notes. I can name that song in 2 notes. Okay, name that song in 2 notes. And it's, what's the minimum number of information you think you need to get that song? These are not the weakest conditions necessary to prove that something is a group. You can weaken these conditions a little bit. Do you need to have both a left and a right identity for the same element E? Or if you know that you have left identities and left inverses, does that give you right identities and right inverses? There are games like this you can play. You are now aware that there are games like this that you can play. We will not be playing those games. If you're interested, happy to talk to you about that as to how much can you weaken these things. Hopefully you've seen a proof of the fundamental theorem of calculus. That the area under the curve is the antiderivative at B minus the antiderivative at A. Whenever I prove this, I usually make the assumption that not only is my function continuous, its derivative exists and the derivative is continuous, because then I can use the mean value theorem and I don't have to use advanced analysis. It just makes the proofs easier. And in all the cases that arise in the first couple of years of undergraduate study, that's enough. It's the same thing here. This is not the weakest collection of items, but it's a good collection. So we have a bunch of things here we can prove. So we have 2 ways to go right now. One is we can be completely theoretical and just prove these results right now. Or I could actually give you an example of what is a group. Because right now we don't have any examples of a group. So which would you like? Second, yeah, let's see what the hell a group is, right? And the more groups you look at, the better sense you have of understanding what's going on. A good example, let's do examples of groups. So, examples of groups. So the first one is going to be the integers under addition. Okay, if I have two integers and I add them, do I get an integer? What would be the identity element? 0. What would be the inverse of n? Negative n. And is addition associative? Yeah. What if I look at the natural numbers? Would the natural numbers be a group or not a group? Not a group under addition. So the natural numbers under addition. Is it closed? Is an integer, is a natural number plus a natural number a natural number? Yes. Is there an identity element? Yes, I consider 0 a natural number, so there's an identity element. Is it associative? Yes. The order in which you add, yeah, I can group however I want, that's fine. But I don't have inverses. What would be the additive inverse of 5? That would be -5, and that's not included. What about the complex numbers? Under addition. Group or not a group? Group. What about clock arithmetic? So I take the numbers, 0, 2, and -1 under clock arithmetic. So since let's call it 11 o'clock now, we'll round up. What time is it in 4 hours? If you had a clock that actually worked like that, what would that clock display in 4 hours? It would display 3. So we're going to say 11 plus 4 is 3 on the clock. We're basically saying 3 and 15 are equivalent because they differ by a multiple of 12. It turns out, clock with, n hours under clock arithmetic. Addition. So, the set would be 0, 1, 2, dot, 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 n minus 1. And, k plus j is equal to k plus j mod n. So we keep, yes,
It's not like here, it's like 3 plus 11, 2, isn't it?
so well, first of all, groups don't have to be commutative.
Oh, no.
They don't. Now, this actually is commutative because 3 plus 11 and 11 plus 3 are the same. They would both be 2. That's fine.
Why is being a video option? Why is it not?
Because not every group is commutative.
So why is it even listed on the?
Because a lot of groups are commutative. So these groups here, these are all commutative. So these are commutative. So we haven't seen a non-commutative group. I do have one in my backpack that I will take out later. Don't worry, there's an air hole. It's breathing. Okay. So we will see a non-commutative group very soon. It's extremely useful to have groups that are commutative. You don't have to worry about the order of multiplication. You don't have to worry about the order in which you combine them. Which means if you have a long expression, you can simplify, you can move things around. But not everything is commutative. So, for example, if I give you, let's do a specific value event. Let's do n equals, 12. What do you think the inverse of 8 is? So what do you think the inverse of 8 as? blank plus 8 equals. So what would be the identity element on a clock with hours from 0 to n minus 1? What would be the additive identity? The n, and n is, we're going from 0 to n minus 1, so n is not on the list. So 0. So what should I add to 8 to get 0? 4. Or more generally, 12 minus k plus k is going to be congruent to 0 mod 12. In particular, what's the additive inverse of 6? Itself. So you can actually be your own additive inverse. Do people want to see a non-commutative group? All right, so let's see. I want to get the video going. So let's see. I can't see it on this, but all right. Does anybody know what this is? It's a Rubik's Cube. It takes me about an hour to teach somebody how to solve a 2x2 cube poorly. No, and the goal is to learn how to do it poorly so that you learn how to generalize this. Like, how many sides does a cube have typically? 6. How many squares on each side? 9. And the way the cube works is, this is a great way to represent a non-commutative group. I can spin things in quarter turns. When you spin, no matter how you spin, everything can be reduced to quarter turn motions. What do you think the identity move would be on a Rubik's Cube? Yes?
Four cycle.
You could do that, but there's something even simpler than a 4 cycle. Do nothing. That's my identity. If I spin left down, what do you think the inverse is going to be? So is it up, right? And so if I give you a sequence of moves, the inverse is going to just be the opposite of each move, but switching the order. Hey, that's kind of similar to what we saw. And then if I do a sequence of moves, followed by a sequence of moves, is that a move? Yes. So that's closure. I've done identity. I've done associativity. Oh, no, I haven't done associativity, sorry. I did inverse. Then associativity, just that it doesn't matter which way you group things. Okay, so this is, trying to understand a Rubik's Cube. There's actually a non-commutative group, a very complicated non-commutative group lurking around this. This is one of my favorite Rubik's Cubes. Is this visible? What do you notice about the sides? Yeah, different. It's 2 by 3. This looks really bad. They're essentially equivalent. Does everybody see that there's a red side? Yes, this is your typical red herring. You don't view it as a red side. You view it like this. It's the 2 reds going into a blue. Or the next one, I could do it as 2 blues going into an orange. If I view it the right way, there we go. It's really the same as a 3 by 3 cube. You just have to hold it at a 30-degree or 60-degree angle. And if you do it like that, you can solve it almost identically as a regular cube. The only difference is, in a normal cube like this, you can't tell if you have a center wrong, if a center is rotated 90 degrees. You can tell if something is rotated on this. So this is the same as a Rubik's Cube with pictures on it. It's a great example of equivalence. It's a great example of a non-commutative group. Oh, I probably should have done the stop share. Okay. That would have been, I should have just done the stop share like that. Okay. Hopefully, just in case it didn't show, I'll just show again, here is the cube. That's much easier to see. And then here is the cube. And if I try to look at it as a red side, that's bad. But if I look at it, red into blue, now you can see there's my 3 by 3. So this is a great example of equivalence. Okay. Go back to showing the screen, which now takes 3 seconds. And we will optimize again. Okay. So I could try to do a clock group under multiplication. But we got to be a little bit careful. Every element is supposed to have an inverse. What should the multiplicative identity be for clock group? Okay. 12 or, well, so 12 should be, that 12 is the additive identity, right? 12 was 0 was the additive. What should the multiplicative identity be? It should be 1. So every element has to have an inverse. Can you think of a number from 0 to n-1 that might not have an inverse? Which number might have trouble finding an inverse? You're finding a multiplicative inverse. 0. So maybe we look at 1, 2, all the way up to n-1. And so the question is this a group? Is it a group maybe for all n or maybe just for some n? So what you would have to do is you would have to check and see, are things closed under multiplication? So what would 4 times 5 be on a clock with 12 hours? So if n equals 12, 4 times 5 is what? 8. And so do you think every number has a multiplicative inverse of n equals 12? So for instance, could you give me a number that's the multiplicative inverse of 5? Is there something times 5 that's going to be 1 mod 12?
So
Itself. And how did you find that?
5 times 25, so it's 24.
Good, but how did you find 5? Yeah.
Split it from 1 to n.
Okay. But how did you know that 5 works? The way I would do it is 1 times 5, nope, doesn't work. 2 times 5, nope, doesn't work. 3 times 5, nope, doesn't work. 4 times 5, nope, doesn't work. 5 times, yeah, 5 times 5 works. What about 7? Anybody think of a number that works for 7? Itself. Let's do one more. What time is it? It's 11 o'clock. All right, so let's do 11. Can anybody think of something that might work for 11?
11.
Okay, so it turns out that when n equals 12, it's a group under multiplication, if you just throw away 0, and every number is its own inverse. Do you believe me or not? I gave you 3 data points. Right, this is the 16 over 64, the 19 over 95, the 24 over, oh, sorry, the 49 over 98. Just because something works a couple of times doesn't mean it always works. I gave you an example where I chose 3 numbers and they were all their own inverse. Does that mean every number is its own inverse? Prove or disprove that. Yes.
2 is not
2. 2 times 2 is
4.
4. So 2 is not its own inverse. Is there any number that works for 2? Is there anything times 2 that's going to be 1 mod 12? Will anything work? So if I want to solve this, that means 2x equals 1 plus a multiple of 12. Can 2 times x be 1 plus a multiple of 12? Why not? Yeah, so this over here is even, this is even, and this is odd. So we know that this is not a group. So this is a no. If n equals 12. So then it becomes an interesting question, for which values of n is this a group? And this is playing a key role that we saw on day one in cryptography. These clock groups under multiplication will play a huge, huge role. So we now have a couple of examples. We have the integers, we have the complex numbers. Matrices under addition would work. Would matrices under multiplication work?
No, because not all matrices have an inverse.
Not all matrices are invertible. So then you might start to restrict to, maybe I can look at special sets of matrices. This is always a danger as to what did you do in certain classes. At Williams, there was one year where the professor forgot to do eigenvalues. He just thought that there was a second course in linear algebra and they would cover eigenvalues then. And you go, wait, there's not a second course? Oh. And so you can imagine, of course, that the department was very understanding and nobody brought this up year after year, decade after decade. Have you guys done orthogonal matrices? If you want to diagonalize a real symmetric matrix, you can do it with an orthogonal matrix. So if you've done orthogonal matrices, those would be a great example of a group. Orthogonal times orthogonal is orthogonal. Orthogonal matrices, their inverse is orthogonal. Everything is great. What if I looked at the integers under multiplication? You know, z under multiplication. Do you think the integers under multiplication would be a group or not a group? No, why not?
There's no inverse.
For which number?
So equals to identity.
So only 1 and -1 would have multiplicative inverses. If I gave you n under multiplication, that would also not be a group. What would be the inverse of 5 under multiplication? 1/5. And 1/5 is not in the set. We do have closure. You know, a natural number times a natural number is a natural number, but we don't have inverses. If I gave you the positive rationals, would the positive rationals be a group under multiplication? So if I gave you positive rationals, is a positive rational times a positive rational a positive rational? Yeah. If I give you a rational a over b, what's its inverse? B over a. Do we have an identity? 1. And it inherits associativity because they're numbers. So z under addition, q plus under multiplication. So the positive rationals would work. So we've got a couple of examples. So let's go back and start looking at proposition 2.9. Should we do A first, or B, C, or D? What do you think? Which should we do first? Usually there's a reason why things are ordered in a certain way. It may not matter, but if you're doing an exam, a lot of times if the professor is nice, A leads to B, leads to C, leads to D. Or sometimes it might be, it helps you build things up. Let's prove A. We want to show C has exactly one identity element. So let's do proof by contradiction. So assume not. So E1 and E2 are identity elements. So what does that mean? So what does it mean for something to be the identity? Well, go back a page. This is the nice thing about doing it by slides, is I can now quickly go back to what we did a moment ago. To be the identity element, it means no matter what G you take, E times G equals G times E equals G. So we know, so for all G in G, G times E1 is E1 times G is G, and G times E2 is E2 times G equals G. This works for any choice of G. We get to choose a G. And so this is where you have to be a little bit creative. What might be a good choice of G for this problem? There are two natural choices. What are good choices for G? E1. And what else? E2, right? So what am I doing? I'm doing a proof by contradiction, and I'm writing down, what do I know? I know that E1 and E2 are identity elements. And so what does it mean to be an identity element? It means no matter what G you take, G times E1 is E1 times G is G, G times E2 is E2 times G is G. This has to be true for every value of G. Can I find a good choice of G? How many of you only applied to Siena? Wait a minute. Yeah, you would have applied to Siena College, even though you attend Siena University. So none of you actually got into the school that you're attending. Interesting. Never had this before. Right? So did everybody here apply to Siena College? Okay. Did anybody apply to more than one school? Did anybody get into more than one school? And then what happens when you get into more than one school? You have to choose. And that can be extremely difficult because typically you don't have one school that beats all the competitions in every category you care about. This school might be better for X, Y, and Z, but worse for alpha, beta, gamma. And then you have to decide which things matter most, and you have to try to find a way to take things into account. The more choices you have, the harder it is. This is really nice. I only know two things in my group, E1 and E2. So when I'm trying to figure out what should I try for G, I've only got two things to try. Without loss of generality, which should we try? Should we try E1 or should we try E2, or does it not matter? Doesn't matter, right? But what do you think most people would try, E1 or E2? Probably most people do. So taking G equals E1 yields E1 dot E1 is E1 dot E1 is E1, and E1 dot E2 is E2 dot E1. That's a terribly written. E2 dot E1 is E2. Okay, what else could we do? We could also, taking G equals E2 yields E2 dot E1 is E1 dot E2 is E2, and E2 dot E2 is E2 dot E2 is E2. Of these four items, which items do you think are useful and which items do you think are not useful? And
Third one.
oh, sorry, this should be right here.
Yeah.
I am taking G to be E2.
Oh.
No,
Yeah.
no, I think that's I have too many E2s. Oh, sorry, this one should be E1. This one should be E1 over here. Right? Because I'm taking G equals E1. So when I have G dot E2 is E2 dot G is G, if G is equal to E1, that should be an E1, not an E2. So I've got four relations here. Which relations do you think are useful? Which relations do you think are not useful? Two are useful, two are not useful. Which ones are useful? Yeah, so the ones that have the different numbers are useful. And then these ones are not useful. Because this just all involves E1, this all involves E2. But this is E2 dot E1 is E1.E2 is E2, and this is E1.E2 is E2.E1 is, oh, that's the same thing. So we have E2.E1 equals E1.E2 equals E1 and E2. So if it equals E1 and it equals E2, what can we deduce? They're the same. Thus, E1 equals E2. So this is a prototypical proof in modern algebra. We always start with, how do we want to do it? Do we want to try to do a proof by contradiction? Do we want to do a proof by induction? Do we want to do a constructive proof? You have to get a sense of how do you want to try to do it. So one thing is, the claim is that there's only one identity element. So let's assume that there are two identity elements and try to get a contradiction from that. All right? Then the next thing is, it's like proving all your derivative laws in calculus. Every proof begins with the definition of the derivative. I want to prove the product rule. I start with what's the definition of the derivative for the product f of x, g of x. And then I start doing some algebra. So I write down, what do I know? Well, if they're identity elements, I go back, and this is what I know about identity elements. I know that E dot G is G dot E is G for any choice of G. Okay, that's for any choice of G. Can I find a good choice of G? And it turns out that there is a good choice of G, E1 or E2. These are the only things we have in play. We don't know anything else. So if I don't know anything else, this is it. Has anybody here taken a good set theory class? Did you construct the natural numbers from the empty set?
I took a foundations of math class. Don't know if
So sometimes what you do is you start off and you construct the natural numbers by, you start off with the empty set. And then the next set you form is the set containing the empty set. And then you can have a new set, which has two elements, the empty set and the set containing the empty set. And you build up, and you start off with the only thing you know, nothing. You start off with the empty set and you build from that. It's the same thing here. I only know about E1 and E2, so I might as well try G equals E1, let's try G equals E2, and just put everything I can think of on the page in front of me. So I've got everything here now, and then I notice, hey, wait a minute, this is the same expression. I've got E1, E2 is E1, and E1, E2 is also E2, and now I'm done. All right, so this is a good place to stop. And so, end the class.